gonna get there. It's in your notes. Okay, we're starting the last chapter here, and we're going to continue what we talked about with acids and bases in the last chapter, and we're going to add a couple other concepts. Titration, and we're going to do some titrations, and we're going to talk about pH, which is the first thing most people know about acids and bases. Well, pH is related to how acidic something is. And when we watched the acid-base film, he talked about the pH of various substances. Most of you have taken a pH reading. Where have you done that in here? Soap lab. You tested the pH of your soap to see if it was safe to use. You can't ever forget our friends, hydronium and hydroxide. And in the last chapter, when we talked about the oldest, most traditional definition for acids and bases, what was the significance of hydronium or hydrogen ions? Arrhenius acids. Yeah, and an arrhenius acid, we said that was something that increased the concentration of hydronium ions or hydrogen ions in a solution. What was the significance of the hydroxide ion in the Arrhenius definition of acids? Yeah, that's something that increased the concentration of hydroxide ions in solution was a base, and that was our oldest, most traditional definition of acids. With the Bronsted-Lowry definition that we talked about later, do these things still show up? Yeah, because typically whatever has donated a proton in an aqueous solution ends up creating what? If you're in water and you donate a proton, that proton gets picked up by water, generally, not always, but generally. And so very often those things that are proton donors or Bronsted-Lowry acids end up increasing the hydroxide ions also. And the things that accept a proton very often accept it from water, and so we end up with a solution with hydroxide ions. So we can't forget those guys. They're very important in this chapter. I know this is exciting news. This is like an ad for Ginsu knives. What if I told you that we could measure the concentration of hydronium and hydroxide ions? Would you pay $19.99? Don't answer yet. We can measure the concentration of these ions in a solution. We can do it. Why would we want to do something like that? This is what pH is based on. pH is actually a representation of the concentration of those ions in a solution. So that random, seemingly random number between 0 and 14 that we usually reference actually represents concentrations of hydroxide and hydronium ions. Okay, so if we remember our old friend water, little Mickey Mouse, we've got oxygen with 2 hydrogens, and we know lots of things about water. Here's the weird thing, hence why the slide says weirdly. If we have 1 liter of pure, absolutely pure, distilled, deionized water, there is nothing in it but dihydrogen monoxide, and we leave it all to its own devices, some of these Mickeys will begin to behave strangely. Bad Mickeys. So, some of these Mickeys will lose an ear and give their ear to another Mickey. And then we have this situation. So we now have, what is this former Mickey? Why, it's a hydroxide ion. What is this former Mickey? Why, it's a hydronium ion. Now, not all the Mickeys will do this. We just get a few mutant Mickeys in every liter of water. But this happens all on its own with no prompting from anybody else. There's nothing else in there that's donating protons or accepting protons. The Mickeys just start trading ears. It's really kind of freaky. So we get a couple deformed Mickeys in every single liter of water. Just pure water, left to itself. Does this not freak anybody else out? Because I think it's just bizarre. And we get this equilibrium. So we have water plus water, reversible reaction, hydronium plus hydroxide. And that reaction right there forms the basis for a lot of things that we're about to do. In every 1 liter of water, so 1 liter full of Mickey Mouses, 1 liter full of dihydrogen monoxides, we get 1.0 times 10 to the negative 7th moles of hydronium. We can figure out how many Mickeys that is, right? we don't really need to unless you feel it necessary. Anybody feel it necessary to calculate how many Mickeys that is? Because I don't. Good, you can do it on your own time. Well, we also get 1 times 10 to the negative 7th moles of single-eared Mickeys, of hydroxide ions. So that makes perfect sense, right? That if this many Mickeys gained an ear, they had to get it from someplace, right? So we would have an equal number of Mickeys running around with 3 ears and 1 ear, because they had to get that 3rd ear from someone. So we have equal numbers of Mickeys with 1 ear and with 3 ears. This is very logical, yes? Okay, good. And unless we have some other weird little species in there, but we don't. This is pure water. Pure water. And this is not a lot of Mickeys. I mean, this is a really small number.
So nothing happens if they never resolve their little ears?
Nope, they don't. Nope. We just get hydroniums and hydroxides. So 3-eared Mickeys and 1-eared Mickeys. Okay, so we'll draw these little guys. Here's our 3-eared Mickey. And here's our 1-eared Mickey. And they do look really sad, don't they? Okay, so we have equal numbers of these two things. What's interesting is, well, a couple of things are interesting. We have a standard notation for showing the concentration of any ion in solution, and this would be true if it was chlorine ions or hydroxide ions or hydronium ions. If we want to talk about the concentration of any ion in solution, we draw a bracket and we put the ion in there. So this would be the notation we would use to represent the concentration of hydronium ions in a solution. Okay. And I should let you know that the amount of self-ionization that goes on changes a little bit at various temperatures. At anything near room temperature, we're going to have that 10 to the negative 7th moles of 3-eared Mickeys and 10 to the negative 7th moles of 1-eared Mickeys. So 10 to the negative 7th moles of hydronium, 10 to the negative 7th moles of hydroxide. So in water, and when we say at 25, really anything near room temperature, so probably a fairly big range, but anywhere maybe between 15 Celsius and 40 Celsius. Anything around room temperature, if it's a temperature that you could imagine walking into a room and that being the temperature, we're probably going to have those same numbers of moles of ions. Well, that leads us to... So if we take the concentration of hydronium ions and we take the concentration of hydroxide ions and we multiply them together, we get something called the ionization constant. And constants in science, as you know, are typically shown with the K. This one is the ionization constant of water, so it is K sub W. So this constant doesn't really change. And we said at different temperatures we're going to get different levels of hydronium and hydroxide ions, but their product is always the same. It's always a constant product. So it is the ionization constant of water. So if we multiply that pretty normal number of moles of hydronium and hydroxide ions together at room temperature, we get 1.0 times 10 to the negative 14th. That's the ionization constant of water. So what we know is we assume that the ionization constant of water is about that at a range of temperatures near room temperature. So that's our assumption. That doesn't change much. One of the numbers may go up or down, but that ionization constant remains pretty. So what are the units for kW? Let's look at this. This concentration of hydronium ions that we're talking about, and this concentration of hydroxide ions that we're talking about, what are the units here? 1.0 times 10 to the negative 7th what? Where have you seen moles per liter before? In doing concentrations. 1 mole per liter is a what? Big M, molar solution. 1 mole per liter is a 1 molar solution. So what we're saying is that the concentration of hydronium ions is 1.0 times 10 to the negative 7th molar. Okay? And the concentration of hydroxide ions is 1.0 times 10 to the negative 7th molar. When we multiply those together, we get 1.0 times 10 to the negative 14th molar squared. Okay? And that's the ionization constant of water. So it's important to know your units for that because we'll do some dimensional analysis a little bit later. But those are the units for the ionization constant. So we've got a value and we've got units for the ionization constant of water. What can we do with that? Well, we will use that ionization constant of water a little bit later to figure some things out. Basically, we'll use that value to solve for other things. Let's stop for a second talking about just the concentrations and talk about what the concentrations mean. So we said that in water at room temperature, the concentration of hydronium ions equals the concentration of hydroxide ions. Whoops. So these two are equal. Because these two are equal, and we consider this neutral. So as long as a substance has equal amounts of hydronium and hydroxide, the substance is neutral. That's all neutral means, is that you have the same amount of 3-eared Mickeys and 1-eared Mickeys, the same concentration per liter of hydronium and hydroxide ions. That's pretty simple. That's not terribly complicated. Okay, so if we have a substance where the concentration of hydronium ions is greater than the number of hydronium ions that we find in just plain old self-ionized water, so greater than 1.0 times 10 to the negative 7th molar, we call that an acid solution. Okay? If it's got more hydronium ions than pure plain old water does, it's an acid solution. If we have something where the concentration of hydroxide ions is greater than the number found in just pure plain old self-ionized water, that solution is considered a base. It's a basic substance. The substance is a base. Okay? So let me ask you, the question is asked in your slides, which definition of acids underlies this math? Don't yell it out, write it down. As we're talking about acids as increasing the amount of hydronium ions in a solution and bases as increasing the amount of hydroxide ions in a solution, that's straight out of Arrhenius. This is old, traditional acid definitions. This predates Bronsted-Lowry. Yeah, so this comes out of the Arrhenius definition of acids, where we're talking only about hydronium and hydroxide ions in solution. So this is clearly related to the Arrhenius definitions. Okay, so if for some solution we have a concentration of hydroxide ions, or hydronium ions rather, I apologize, that is equal to 1.0 times 10 to the negative 5th molar concentration, is that solution an acid or a base? Is that substance an acid or a base?
Acid.
It's an acid. Because, and this is where these do get tricky, these are negative exponents, so 1.0 times 10 to the negative 5th is greater than 1.0 times 10 to the negative 7th. Don't forget that. That's an easy way to screw yourself up. So that would be an acid. Okay, so for some other solution where the concentration of hydroxide ions is 1 times 10 to the negative 4th molar, would that be an acid or a base? It's a base. Because, again, don't be fooled, these are negative exponents. 1 times 10 to the negative 4th is greater than 1.0 times 10 to the negative 7th. So this is a base. Okay? Does that make sense? You have to be real careful with those exponents. The negative exponents do tend to screw people up, so be careful with that. Okay, so that is where we'll end today. And I will assign a few homework problems, which will be due, well, we'll see. So let me get a few homework assignment problems on, and that's it.